we're now going to tackle the grade 11 chemistry. I'm going to just start with basic, just building up the building blocks that we're going to need for this process. Essentially, you've seen the periodic table and been introduced to it, and the things that happen across the periodic table, and the different kinds of things like diatomic gases and these molecules reacting with that, and chemical equations, and putting them all together, okay? Which essentially is pretty much what we do every time we do something in the kitchen. We chuck a whole bunch of chemicals together, put it into the oven and heat it, and you get a cake or whatever you're doing out of it, right? So it's the addition of the chemicals together. But before that, we need to know, why does this happen? I mean, why do we have hydrogen or nitrogen or whatever as a diatomic gas? What is so special about the noble gases? They're inert, right? What's it all about? Essentially, as we've said in the physics section, and we'll repeat ourselves probably ad nauseum, it's keeping track of what the electron is doing, where the electron is at any point in time, and why it moves from one point to another, what pulls it that way or the other way. If you go back, if you remember, we did in electrostatics, we did Coulombs Forces, where we found that there's a force of attraction between charged particles, or a force of repulsion. Do you guys remember that section? We said that we had a force, the Coulombs force. We had force is equal to K Q1 Q2 over R squared. Remember that? And these were the charges. If we had a plus and a minus, remember, a plus and a plus, we got repulsion, and a minus, we also got repulsion. The others, we got attractive forces. So now let's consider two independent atoms, okay? Let's say, for example, it's hydrogen and hydrogen. Now, we know it's diatomic, right? But how did it get to be diatomic? What is actually happening inside there? Well, if you remember, on the periodic table, each advancement from hydrogen to helium and so forth entails the filling up of an orbital. Remember the Aufbau principle and those, where we had the spins and the orbitals getting filled up, right? So if we, for example, took hydrogen, we know it's got one electron, and helium is up there. It's got 2 electrons. Now, if we go back, remember we had the different energy levels, first level, second level, third, and so on, all the way up, and we can go quite a long way up into the energy levels. What is essentially happening is we are building up a universe, if you like. We're building up planets around a central core atom, around the protons in the core. These electrons are building up and sitting at different layers above there, okay? Different energy levels relative to the one below or relative to the center, okay? So we think of it in terms of a solar system, I guess, is one way of doing it. And we know that in the first orbital, just to revise, we had an s orbital. Then in the second level, okay, over there, remember we had one s, and we could only fit 2 electrons in there, right? It's a tight parking area. We can only do 2 in that section, right? But now, if we think about it, right, we've got our core, where we've got our protons in there, and we've got our electrons flying around out here, okay? You remember, in the S, they're actually pretty close, aren't they? So think of the electrostatic forces over there, okay? Got our protons here, and the electron is sitting up here like this. If you think of it as a tennis ball, that surface on the outside, what have we got? We've got a force between the electrons and the nucleus, a force of attraction, which means how tightly is this being held on, okay? Then we go to helium, we've added another one, it's still floating around on that surface. Now we go to the next level up, and remember, we added into the 2s, 2p, we start filling the p's up, remember? And this is level 2p, 2s2 is full, and 2p can handle, it's got 3 garages, 2 cars, it can handle 6. So we can have 8 in the outer shell. But think of it like this, what is happening? we've got our protons here, right? And don't forget, each time one of those, we get an extra proton sitting in there too. What is happening? These electrons are very close, right? Then we're another level up. Then we're another level, and we keep going up a level. So what is happening is that although we've got the force of attraction over here, we're getting further and further away because these electrons here make sure the next go up, and the next go up, and the next go up. So they keep going up in the shells, don't they? So what we're doing is we're packing extra levels onto it. Well, in essence, what are we doing? We are increasing that. Well, we know that the charge here and the charge there are both 1.6 times 10 to the minus 19 coulombs, right? Which is the electron, the proton. The radius is getting further. And we know that the force of attraction diminishes with the square of the radius, right? Which means it's getting less quickly. So the further we are away, the further out those electrons are. Okay? And that means that they're not held on as tightly. Okay? Just in principle. All right? Let's not get into the actual charges and the detail. But if we just think the further they are away, do you know what? Pluto sitting out there isn't as strongly held as Mercury, Mars, or even us, who are very close. Right? So we have to think about it in terms of the levels that they are at. Right? So now, let's think of, we've now got a hydrogen atom, all right? Let's just bring our hydrogen atom, all right? We've got a hydrogen atom over here, right? Here it is. We've got our positive here, and we've got our electron over there. Let's bring another hydrogen atom closing into this one, right? Can you see, and I like making use of my lollipops. They're twofold. One, they serve very nicely as atoms and molecules when I put them together. And secondly, you can eat them afterwards, which is quite cool. Now, what we've got is we've got two independent hydrogen atoms over here, right? It's got its proton, it's got its electron, it's got its proton, it's got its electron. Let's bring them closer together, right? What is going to happen? The forces are now starting to, the electrostatic forces, if they are, we rather just use a different color for this one. Okay, because I just want to draw a graph because you may have seen it in yours. They're sitting far away from each other. So we've got our things sitting over there. They're pretty far away, right? So they are independent, right? So let's assume, or let's pretend that they have a zero energy state, all right? As we bring them closer and closer together, what is happening? They're getting closer and closer. At some point, the R becomes effective, doesn't it? Right? What do we have? We have a situation of two negatives, positives. We have a situation of a repulsion, right? So we would then say, I'll explain what I mean by this now, is this. As we bring them closer together, right, at some point, okay, we are going to find that not only is this attracting this one, but it also starts attracting that one, right? In other words, the whole repulsion attraction scenario resolves itself into one which is mutually beneficial, right? We get to the low energy state. That is where these two are at the right point, just close enough together, where we've now balanced out the repulsions and the attractions. And what has happened is that we've got that. This guy has also, okay, got his attraction to that one there. And we have a situation where these two electrons essentially become shared between the two hydrogen atoms, right? They come together and they coexist together. The protons are at the right distance apart, and the electrons are then shared out on a new surface, right? So if you think of it, it's like bringing two tennis balls together, right? initially they repel because of the electrons, and then suddenly they form one single tennis ball. So, and I mean really, we're just talking hypothetically here, all right? It's going to look, right? We're going to have our central core there, our plus and our plus, and we're going to have, let's just change it to red over here. We're going to have the electron doing that, where they actually become shared with each other, all right? And the electron then sits on a new surface here and over there. So the two electrons go whizzing around on a new surface, okay? This is where we've got a nice balance between the electrostatic forces of attraction and repulsion. It puts us at the low energy state, which is down here, okay? Now imagine we keep pushing them further and further, rather closer and closer together. What are we doing physically? Okay, physically we are now trying to actually push these two protons together, aren't we? The electrons are on their shell, on their surface. They're shared out, so they're happy. But now we're starting to push the protons together, right? So as we get closer and closer, so the force of repulsion becomes more and more, and the more and more energy we have to do to try and get that to happen. It's not a natural state because everything's trying to exist in its most, let's say, the laziest possible state it can. Okay? It's trying to just hang out there and just chill, right? So as we keep pushing them together, so if we go back to the graph, all right, what are we doing? We are now sending the energy skyrocketing because we're trying to push two protons, now they're protons, right together like that, and they don't like that. So the forces become very strong in repulsion, okay? It's not a natural state of affairs. They don't want it to happen, okay? So that's how we get this process going of putting these electrons together. Now, if you think, for example, okay, helium, you don't get helium. It's already full. Its parking areas, it's 1s2, isn't it? Right? So if you've got helium over here, it's already got 2 electrons, like that. It doesn't want any more. It doesn't have another orbital up here that it wants to share. There's no more electrons. So it's full. So it puts up a parking area full sign, and it says, thank you very much, not interested in any further electrons. Okay. Now, this sort of process brings us to just let's go over very, very quickly the valence electrons and the valency. Let's take nitrogen as an example, shall we? All right. Now, we've got nitrogen, and if we go onto the periodic table, I just want to erase that guy. We go onto the periodic table, okay, for nitrogen, and we can have a look, and we say nitrogen is, find my periodic table, nitrogen is number 1, 2, 3, 4, 5, 6, nitrogen is number 7. Guys, there's no reason why you can't count it, okay? So we say, right, nitrogen, you have got 7 electrons. Right, let's put you guys in, okay? 1s2. There we go. There's 2. Then we go up to 2s and 2p. What do we fill first? We fill the 2s. Then we fill the 2p. How many have we got? 7, 4, which means that we've got 3. So essentially over here, we've got a vacancy, haven't we? We've got open parking spots for 3 electrons, okay? Now, let's just think of it as the outer shell here, right? The outer shell over here, okay? Those are the outer shell. This is the core, okay? These are very tightly held, remember? Okay? And what is happening is that the electrons are the things that are moving around. The same as the static electricity. The electron, we rubbed it off and put it onto something else. Here, the electron is going to move from one to the other, okay? Or be shared between them, depending on what it becomes. We have got 3 there, right? Now, what does that mean? It means essentially that we have a valency. There's 3, right? And we know it's a nonmetal, so it's got a -3 valency. Okay? But the valence electrons are the ones in the outermost shell. So my valence electrons are these. Okay? So when we're doing this, you've got to be careful that you identify the valence electrons and the valency. It's a different thing. The valence electrons are the ones that are there in the outer shell. They're the ones that are likely to react because they're far enough away, let's say. Then we've got a valency of -3, which means I will take electrons. Okay? So your nitrogen, remember, fluorine, oxygen, nitrogen, those are your -1, -2, -3s, because your noble gases, your inert gases at the end, your helium, neon, argon, krypton, xenon, all of those guys, those are full up in an octet structure. Okay? There's no parking spaces available. Okay? Now, what we do is we represent this in terms of what's called a Lewis diagram. How do we do that and why do we do it? Guys, it's just a diagram to help us to visualize what is available to bond, and then we're going to look at how it's going to bond. Okay? Well, let us take now our nitrogen over here. How do we draw this diagram? So, right, here's nitrogen. Okay? Well, let's start. We've got to put in the outer shell. So we go 1, 2, 3, 4, 5. Right? There we go. 3 there and 2. So we got 5 in the outer shell. And you can see all I've done is diagrammatically represented, right, where there is a space. Right? So we've got those spaces there. Which means that electrons can come in and fill those spaces, and thus it can bond with something else. Because the bonding process is essentially electrons moving into open spaces. All right? Now, just before we move on to that, let's take, for example, let's pretend this suddenly is not hydrogen, this is now nitrogen again, right? Just picture this, right? We've got in the middle here, we've got our nitrogen. Now, those are our 3 parking spaces there, right? What we've got is we're trying to fit an electron into a gap. Can you imagine how difficult that is? Why? Well, because, first of all, these electrons, these are randomly flying around. The nitrogens, the hydrogens, they're randomly flying around. Now we take an electron, which is a small little thing, right? And we say, hold on, you must now go into that parking space over there. You know how tiny an electron is. You've seen how much it weighs. What's it? 9 times 10 to the minus 31 kilograms. It's incredibly small. And they're all moving around. So we say, hang on, here we go. I'm going to throw you off and put you onto there. So I'm going to come along here and hello, we're going to share an electron and do that. The probabilities are just immense, okay, of doing that. So we have to do certain things to make this happen. Right? That's going to be dealt with in time to come. But it's just something to think about and just to ponder, right? Because we're trying to make tiny, tiny little things fit into tiny, tiny little spaces, right? It's a bit like a needle in a haystack. Okay? So now we've got the Lewis diagram for this nitrogen atom. Now along comes another nitrogen atom next door. All right? And we've got him, 1. I'm just going to draw it like that now because we know how many there are. He's got that. But that's confusing me. So I'm going to change it, right? I'm going to change it and I'm going to make it a dot. Okay? The only reason I'm making it a dot is because I don't want to be confused with the guy next door, right? There we've got 3 possible bonds there, okay? So this needs 3, this needs 3. But remember, these are all electrons, right? So this is an electron here, this is an electron, this is 1, this is an electron, They're all electrons, aren't they? So hold on. Nitrogen can come along, right? And it can say, but I need 3 electrons. Okay, I'm unhappy. I'm unfulfilled. I need 3 electrons to live. This one says, I need 3 too, because I'm also unfulfilled. So what do? They said, hold on, maybe we can come to an arrangement here, and we can get together and keep ourselves happy by forming something, and then we are fulfilled because we are putting our electrons together, right? Well, hold on. This guy has got 3 parking spaces. This one's got 3 electrons. So what do? Well, that's pretty logical, isn't it? They do exactly what anybody would do. They say, okay, we will get together. And what happens? They essentially, this guy comes in and shares his electrons. So we get nitrogen bonding, essentially, with a triple bond to another nitrogen. Why triple? Because it's bonded with 3 electrons in the parking spaces. Okay? If we look at hydrogen in the same context, all right, we had a hydrogen molecule coming along. Remember, he only had 1. We had a hydrogen molecule, only had 1. These 2 can share, and we could write that as hydrogen is bonded. Okay? Remember, hydrogen was a +1. Let us take, for example, fluorine, shall we? Fluorine or chlorine, whichever. It's just that fluorine is easier to draw. There's less on my diagram that I have to do. Okay, we will do some of them though. Fluorine. Okay. Where are you? You're number 1, number 2, 3, 4, 5, 6, 7. It's number 9. Right. So fluorine is number 9. But now I say, but hang on. 1s2. This is for fluorine. Okay. 2s2. And 2p, I've got to have 9, 5. So can you see, if I drew this out, I've got 1, 2, 3, 4, 5. There is my open parking area, right, over here, to put another electron in, isn't it? That's what we've got over there. And you can get it from just counting the electrons and knowing how to put them into the diagram, okay, or into the little parking spaces. So let us now take fluorine. Well, fluorine, all right, in its outer shell, okay, it's got 5. It's got space for 1, hasn't it? Right? So what happens? Fluorine, another fluorine comes along, right? And it says, well, I'll tell you what. You let us share this one that we've got over here. We've got this guy all on his own. Let's share it. So what do? He says, okay. And he says okay, and they get together, and once again you've got a single bond between the fluorine and the fluorine. They're sharing that electron, same as the hydrogen is sharing it, right? Can you see what we've made here? This is how we've made H2, right? How we've made F2, isn't it? That's essentially all that we're doing, right? And we said, now let's have a look at the valency and the valence electrons, shall we? Okay. This is what we've got on the outer shell, okay? We had 7 on the outer shell, didn't we? Okay, so if I had to put them in, I would have put in 1, 2, 3, 4, 5, 6, 7. Oops, sorry. 2, 4, 6, 7. There we go. Right? There's my 7 electrons in the outer shell. There is the single parking spot that's available. And fluorine on this side has got the same. So the fluorine on that side would have had, okay, that one has now gone across, 2, 4, 6, and there's its 7th. So we formed F2. Let's go and have a look. How did we form oxygen then, shall we? We've done nitrogen. Let's look at oxygen. What is oxygen? Oxygen is just before fluorine, but let's count it. 1, 2, 3, 4, 5, 6, 7. Oxygen is 8. So if I look at an oxygen, I'll go 1s2, 2s2, and 2p. I need a total of 8. I've got 4, 2p4. Let's have a look what it looks like. Okay, there we go. 1, 2, 3, and 4. What have we got here now? We've opened up 2 parking areas, haven't we, for electrons. Let us draw the oxygen. Okay, let's draw the oxygen. Say, okay, there's my oxygen. Now I come along and I say, right, I need to draw 6 of you. So I'm going to say 1, 2, 3, 4, and I'm going to put 5 and 6 over there. This is just for my diagrammatic representation. Okay. Then I've got another oxygen coming along here. I'm going to put that one in red, and I'm going to put my 2, 4, 5, 6. Can you see now here, between the two, let's have a look. What have we got? We've got, there's a possible sharing, and there's a possible sharing. So what happens in this case is that the oxygens get together, and they form a double bond, which has got 1 electron over there, an electron over there, which is got oxygen there. They have bonded, 2 electrons have come in, so it's come along and it says, right, those have come together with an electron and another set of electrons come together over there. That's where and how these things, this is a lot, remember, from last year, right? But you can see how the diagrammatic representation is just, we draw the symbol of it, we look at the valence electrons on the outside, and we put it in. Okay? It's really as simple as that. Okay? I'm going to carry on with this in the next section. That one is a bit long, but I think it's worth it to lay the foundations very well, because the electron and understanding this process that we're busy with now, that's the critical part when we get to things like electrochemistry in grade 12, where we need to see how electrons are actually moving between things. When we start to move into understanding moles and how the stoichiometry works, it's essentially we're taking a bucket of electrons and moving them to somewhere else, if it's a redox. But this is the process we're going with, and don't forget that a mole of electrons is the same as a mole of anything else, but we'll deal with that in the next section.